Welcome to a lesson on the properties of congruence. Let's begin with a review. From the last lesson, we say A is congruent to B modulo n, and we write A is congruent to B mod n, provided A and B have the same remainder when divided by n. In other words, provided A and B belong to the same remainder class, modulo n. Using congruence and divisibility, for any integers a, b, and n, we have A is congruent to B mod n if and only if n divides A minus B. And using congruence and equality, we have, for any integers a, b, and n, A is congruent to B mod n if and only if A is equal to B plus k times n for some integer k. This indicates that A is equal to B plus some multiple of n. We said earlier that congruence modulo n behaves in many important ways the same way equality does. Specifically, we could prove that congruence modulo n is an equivalence relation, which will require checking the following three facts. Given any integers a, b, and c, and any positive integer n, number 1, A is congruent to A mod n. Number 2, if A is congruent to B mod n, then B is congruent to A mod n. And number 3, if A is congruent to B mod n, and B is congruent to C mod n, then A is congruent to C mod n. In other words, congruence modulo n is reflexive, symmetric, and transitive, and as a result is an equivalence relation. And now let's discuss congruence and arithmetic. Suppose A is congruent to B mod n and C is congruent to D mod n. Then the following congruences mod n are also true. Number 1, A plus C is congruent to B plus D mod n. Number 2, A minus C is congruent to B minus D mod n. And number 3, A times C is congruent to B times D mod n. Notice this is not the same as equations since C and D don't need to be equal, but need to be congruent modulo n. Think of the congruence as being basically equal if we have two numbers which are basically equal, and we add, subtract, or multiply basically the same thing to both sides, the result will be basically equal. This seems reasonable, but is it true? Let's take a look at a specific example. Suppose 29 is congruent to 21 mod 4, and 10 is congruent to 6 mod 4. Let's first verify these are true. If 29 is congruent to 21 mod 4 is true, then 4 must divide 29 minus 21. The difference is 8. 4 does divide 8. And if 10 is congruent to 6 mod 4 is true, then 4 must divide 10 minus 6, and 4 does divide 4. And now let's apply the arithmetic properties above, where A is equal to 29, B is equal to 21, C is equal to 10, and D is equal to 6. For number 1, we have 29 plus 10 is congruent to 21 plus 6 mod 4. Simplifying, we have 39 is congruent to 27 mod 4. This is true as long as 4 divides 39 minus 27, which is 12. 4 does divide 12. 12 divided by 4 is 3. For number 2, we have 29 minus 10 is congruent to 21 minus 6 mod 4. Simplifying, we have 19 is congruent to 15 mod 4, which is true since 4 divides 19 minus 15, or 4 divides 4. And for number 3, we have 29 times 10 is congruent to 21 times 6 mod 4, which gives us 290 is congruent to 126 mod 4. Checking to make sure this is true, we need to check to make sure 4 divides 290 minus 126, and 4 does divide 164. 164 divided by 4 is equal to 41. Before we go, let's prove A plus C is congruent to B plus D mod n. To do this, we use a direct proof with congruence and equality, which states A is congruent to B mod n if and only if A is equal to B plus k times n for some integer k. So to start the proof, suppose A is congruent to B mod n and C is congruent to D mod n. That means that A is equal to B plus kn, and C is equal to D plus jn for the integers k and j. And now we're going to add these two equations together, which gives us A plus C is equal to B plus D plus kn plus jn. Now looking at just kn plus jn, there's a common factor of n. We can write this as the quantity k plus j times n, which is just some multiple of n. Subbing this back into our equation, we now have A plus C is equal to B plus D plus the quantity j plus k times n. which is what we needed to show. In other words, A plus C is congruent to B plus D mod n, and the proof is complete. I hope you found this helpful.